Hello everyone, let's analyze. So, if you remember the first day of lecture, we talked about the square root of 2 and whether that was even a number. Because it's irrational, we can't write it down in fraction form or decimal form. So how can we express this number? We knew it was between 1 and 2 because 1 squared is less than 2 and 2 squared is greater than 2. So if you remember the very first day, we had the idea of taking this search space of the interval 1 to 2 and trying a halfway point, right? 1.5. 1.5 was too much, so we limit our search space to 1 to 1.5. We cut that in half. 1.25 was too little, and we continued in this process until we got closer and closer to a number that when squared ought to be 4. Ought to be 2, I'm sorry. But every number in that sequence was rational. And the square root of 2 is irrational. That means we never actually arrived to the square root of 2, but it makes sense that the square root of 2 ought to be a limit of this sequence because this sequence gets arbitrarily close to each other. So what do we call such a sequence? A sequence that gets closer and closer to each other. We call it Cauchy. So a sequence is Cauchy if, and only if, because it's a definition, for every positive epsilon, there's a natural number n for which the following is true. If both little m and little n are greater than or equal to big N, then the distance between an and m, in other words, the absolute value of an minus am, is less than epsilon. So let's give an example, and of course the example is the one I started with. We know the square root of 2 is between 1 and 2, so we cut our interval in half to get closer and closer. All right, so let a1 be 1 and b1 be 2. All right, remember the interval 1 to 2 is our search space. We're going to look for the square root of 2 between 1 and 2. So x1 is halfway, right? Between 1 and 2, that's 3 halves. Since x1 squared is 9/4, which is greater than 2 by a quarter, right? Then we set a2 to be a1. In other words, the left end of our search space remains the same. And we set b2 to be x1, 3 halves. So now our search space is 1 to 1.5. We cut that in half and we get 1.25, or 5/4. And we continue. xn is halfway between an and bn. If xn squared is greater than 2, we let xn be the right side of our new search space, and the left side remains the same. Otherwise, if xn squared is less than 2, then we set the left end of our search space to be xn. And we repeat forever. And if we repeat forever, we can build a sequence, right, that we would hope converges to the square root of 2. Why do we think it converges to the square root of 2? Well, because each entry of our sequence is sandwiched between an and bn, and an and bn get arbitrarily close to each other. Furthermore, our search space, the interval an to bn, is nested inside previous search spaces. In other words, the interval an to bn is inside the previous search interval, which is inside the one previous to that, which is inside the original. Right. Furthermore, the lengths of these intervals are halved. Right. bn minus an is half the length of the previous interval, which is a quarter the length of the previous to previous interval, right, which is 1 over 2 to the n minus 1 of the original search interval, which is a distance 1. Furthermore, for every little n bigger than some big N, x little n is inside the search interval a and b, and in fact, by definition, it's halfway. Right, we see over here it's halfway. But because these intervals are nested, that's contained inside of the interval an to big N, because little n is bigger than big N. That implies that xm minus xn is less than or equal to 1 over 2n minus 1 for every little m and little n bigger than big N. Since this right-hand side can be made arbitrarily small, in other words, for every epsilon, there exists an n for which this is less than epsilon, we've just proven that our sequence is Cauchy. It's a sequence that gets arbitrarily close to each other. Now, an important note here. What if we lived in a world of the ordered field of rationals? What if we only lived in this world? By the way, Pythagoras thought he only lived in this world. And he thought anything not of that world was heresy, which is why when Hippasus proposed that the square root of 2 is a number and was not rational, he was sentenced to death. I hope that by now we're a little bit more enlightened in that. So, if we lived in a world of the ordered field of only rationals, then this sequence would still be Cauchy, because the sequence gets arbitrarily close to each other. But it wouldn't have a limit in this world because the square root of 2 doesn't exist in that world, because it is not rational, it's irrational. A theorem. Every convergent sequence is a Cauchy sequence. Now, if we think about that statement, it should be self-evident that every convergent sequence is a Cauchy sequence. Well, let's think about that for a second. What is a convergent sequence? A convergent sequence is a sequence that gets arbitrarily close to a limit. Well, if the entries get arbitrarily close to a limit, then they must get arbitrarily close to each other. Right? In fact, if I have a sequence and an infinite number of values are within epsilon of the limit, right, then those values that are within epsilon of the limit are at most 2 epsilon from each other. So let's look at a careful proof. I hope that the idea appears straightforward to you. How do we express this as a formal proof? We'll assume an converges to big A and let epsilon be greater than 0. To show the sequence is Cauchy, we need to find a big N so that if little m, and little n are bigger than or equal to big N, then the distance between an and am is less than epsilon. Well, consider the number epsilon over 2. That's a positive number. So for that positive number, there is a natural number n that guarantees that for every little n bigger than or equal to big N, the distance between an and a is less than half of epsilon. It's also true that the distance between am and a is less than epsilon over 2, so long as m is bigger than or equal to big N. Now let's consider the distance between an and am. What we'll do is inside the absolute value, we're going to add and subtract a, which has the net effect of adding 0, which retains equality because 0 is the additive identity. Then we can take this inequality, right, and we can take this absolute value, right, and we can get an inequality by applying the triangle inequality. The distance between an and am by triangle inequality is less than the distance of an to a and am to a. But this distance, remember, because little n is bigger than big N, that distance is less than epsilon over 2. This distance is less than epsilon over 2. But remember that M is also bigger than or equal to big N. So this distance is also less than epsilon over 2. And of course, half of epsilon plus half of epsilon is epsilon. So we've just shown that for every little n and little m bigger than or equal to big N, the distance between AN and AM is less than epsilon. And we've just shown that our sequence satisfies the definition of a Cauchy sequence. So every convergent sequence is Cauchy. Now that begs the question, is every Cauchy sequence convergent? If it's true, then we've just proven our bisection algorithm actually does converge to the square root of 2. So is every Cauchy sequence convergent? Well, to find the answer to this, you'll have to stay tuned.